Introduction to concavity. Objectives. By this lesson, you should be able to define concavity informally and formally, define and be able to find inflection points. Given a detailed graph of f of x, find the intervals of concave up and concave down. Determine where a function f of x is concave up, concave down analytically using mathematics. Determine whether a function f of x is concave up, concave down. Find the initial points given graphs of f of x and f double prime of x. F prime of x is the hardest one. This one's easy. That one's not too bad. This one's the difficult one. Okay, let's talk about informally what a concavity means. Concavity, all it is a function is concave up on interval if it is upward facing. So if it's opening up, like right here, right? Concave up. A lot of people say if it could hold water, then it's concave up, right? If you could fill a little bit of water right there. If function concave down, if it's downward facing, if it's opening down. So like right here, so it's opening down. That one cannot hold water. And we also need to talk about, so that's what concave up means. This opens up, concave down is where it opens down. We also need to talk about the point of inflection right here. This is where it switches from concave up to concave down, or from concave down to concave up. Now, point of inflection is a point. I know when we talk about inflection points, we really don't, when we talk about critical points, we really don't, the critical point's a funny thing because we talk about the x values. Point of inflection, we actually want a point. So it should be a point C with f of C, the x and y value. So it is a point. And it's just where it changes concavity. It's the point right there. Formally, an inflection point was formally, let f of x be a differentiable function of open interval AB, then f of x is concave up on AB if, so it's concave up. Let's look at the slopes here. So we have this concave up. Notice I put lines here. If you look at the slope here, it's like a negative slope. It's opening down. Its slope is down. Then we have like a zero slope. Then we have a positive slope. That means your slope is increasing. We're going from negative to positive. So all concave up means is your derivatives are increasing or your slopes of tangent lines, your tangent slopes are increasing. And similarly, if you look at concave down, it's going from, so right here we're positive slope, then we're zero slope, then we're a negative slope. So you can say the derivatives are decreasing or the tangent slopes are decreasing on the interval A to B. So again, that's the formal definition. Formal definition of concave up is the tangent slopes are increasing and the concave down is the tangent slopes are decreasing. Again, most times I just think of open up, open down. Opening up, concave up, opening down, concave down. So let's say if I give you a graph here. So here we have about the following graph of f of x. Identify the inflection points on the intervals and the intervals of concave up, concave down. So just here's a graph of f of x. There's this funky looking graph. All I know where it's concave up and where it's concave down. We'll do concave up in blue and we'll do concave down in red. Alright, so let's look at the graph. This one, opening down, right? So let's say it's concave down. Then we have opening up, opening up, opening down, so another concave down. So let's put minus and minus. Let's do concave up ones now, right? From here to here is opening up, plus, and opening from here to here, opening up, plus, and then from here to here, opening up, plus. So concave up. It was concave up on all the plus signs from A to B, and then from B to C. And then finally from D to infinity. It was concave down all the red signs, so from negative infinity, I guess arrows at the end, to A, and then from C to D. Like that. So concave up, concave down. And where's the inflection points? You kind of see them already highlighted on the graph. They're right here. at a and f of a, and then right here at d and f of d. Those are my inflection points. And then this is not, we'll talk more about y in a second. This one, if you see it's not really a point, it doesn't switch signs, right? Remember, inflection point has to switch from concave up to concave down. Over here it doesn't. So right here it does, but then it's not like a point. It's like a not continuous graph. It has to be differentiable, so not there. Same thing for there actually, not differentiable, so it can't be an inflection point. Theorem. Yay. Let f of x be a differentiable function on the interval ab, then f of x is concave up if the second derivative is greater than 0. Positive. So, right, this relates the concavity to the second derivative. So, concave up, it's a lot like when you do monotonicity, increasing, decreasing. Concave up is when the second derivative is greater than 0, and it's concave down when the second derivative is less than 0, or negative. So, super important here, right? Now we know, hey, if you want to find concave up, it's just when the second derivative is greater than 0. If you want to find concave down, it's when the second derivative is less than 0. Very important. Very, very important. Test for inflection point. So what we do is we assume f double prime of x exists for all x in the interval, and we let c be the interval. If f double prime of c equals 0 or does not exist, then that's complementary. And here's new, if double prime of x changes signs at x equals c, then f of x has a point inflection. So what does that mean? It just means this. If you want to find an inflection point, we got to do a couple of things. We got to set the second derivative equal to 0, or undefined. Those are our possible inflection points. And then we have a second criteria. We actually have two criteria for an inflection point. First, with the second derivative has to equal to 0 undefined. And then second, it has to change signs. At x equals c has to change signs. What's that about? Well, remember our graph from earlier? Right here, right? Remember, the inflection points, we only had two inflection points because there were only times where it changed sign. It went from concave down to concave up. This went from up to up, not an inflection point. This one did change signs, but that's why I said it's possible because the second derivative does not exist here. So it failed the first criteria, actually. And then, in this case, it changed signs again. Okay, so now let's talk about how to find the inflection points and intervals of concavity. Now, this is actually similar to doing monotonicity, increasing, decreasing. First, we're going to find all x values where f of x, the double prime of x is equal to 0 undefined. Right? These are our possible inflection points. And remember, not all of them actually work. Plot the possible inflection points on a number line to break it up. You could graph it, but honestly, with inflection points, it's a lot easier to do just do a number line because the graphs can get kind of funky. And it's like before, we just do a sign chart, pick test points in each interval, and then notice since we're doing it for the second derivative, we plug them into a second derivative. It's the key thing about sign charts. If you do a sign chart for the first derivative, you plug your test points in the first derivative. You do a sign chart for the second derivative, you plug your test points in the second derivative. Don't overthink it. If the derivative is positive, then it's concave up. If the derivative is negative, it's concave down. If concavity changes between the intervals, then it's also an inflection point. So that's it. Basically, we just do a sign chart for the second derivative. That's all. So let's do that here. Let's do a couple examples. Find the points of inflection of f of x equals 3x to the 5th minus 5x to the 4th plus 1, and determine the intervals where it's concave up and concave down. So first thing I do is I got to take a derivative a couple times. So here's our first derivative. So 15x to the 4th minus 20x to the 3rd. Now again, if I want to increase and decrease, this is what I work with. If we want the inflection points, we take a derivative one more time. I get 60x cubed minus 60x squared. Now we're going to set it equal to 0 or undefined. Lucky for us, this only has the zeros. Right, we factor it. These both have a 60x in common, x squared in common. I get x minus 1. I split it, and my possible inflection points are x equals 0 and x equals 1. Now again, if you want, you could graph that. If you know how to graph it, and just keep in mind, like if you could graph this, it does work. We have 1 here. We have 0. Keep in mind 0 has a monotonicity of 2, so it actually bounces. This is positive, so it kind of go like this. So if you're prographing, it still works. But I think for most people, they actually prefer the sign chart in this case. So we're going to do a sign chart. Again, this is for the second derivative. I always like to label it so I keep track of where I have to plug it into. We have one at 0, and we have one at 1. Right, so my intervals are -infinity to 0, 0 to 1, 1 to infinity. We're going to pick some test points. So things to the left of that, like -2. Something between those two, that kind of sucks, 1/2. Something to the right of this guy, 2. Now remember, we're talking about the second derivative here. So we're going to plug our test points into the second derivative. So either this guy or the factor version works here. Right, I didn't move anything over, so I'm still good. Remember that trick I taught you before? Notice this? It's squared, so this is always positive. So really, all I gotta do is plug my test points into this guy. If it's negative, then negative times negative is negative. If it's positive, positive times positive, positive. So that's all I gotta do. So let's start with the first one, -2. Plug -2 in there. You're gonna get -2 minus 1 or -3. -3 times a positive is a negative. Then we do 1/2. Again, all we really care about is plugging this guy. Now all you care about is the sign also. Plug 1/2 in here. 1/2 minus 1 is a -1/2. Well, a negative times a positive is a negative, so this is also negative. Then we have 2. Plug in 2. 2 minus 1 is 1. Positive 1 times a positive is a positive. So we have a couple things, right? Let's talk about concavity first. Concave up, that's where it's positive, so it's this guy right here. So 1 to infinity. Concave down, that's both of these guys, and just like before, it stops at 0, so we're going to say from -infinity to 0, and then from 0 to 1. Because 0 is neutral. Or I should say, x-intercepts are neutral. So it's concave down from there to there, and from here to here. Now we're going to talk about inflection points. So look at my inflection points. Remember, when it changes sign, it's an inflection point. So if we get this first one here, negative, negative, not an inflection point. Did not change signs. Right here, though, from negative to positive, it did change signs, so this is an inflection point. So we have one at x equals 1. But keep in mind, what I said before, right? This is actually an inflection point. They actually want a point here. So my inflection point, x value is 1. You got to find the y value, though. And since it's a point, if you want to find the y value to point, you always plug it into the original function. Right, so if you want an actual point, it has to go to the original function. So we're going to plug 1 in there. So f of 1 is equal to 15, 3, 1 to the 5th, minus 5, 1 to the 4th, plus 1. I get 3 minus 5 plus 1. I get -2 plus 1 is -1. So my inflection point is at 1, -1. I know, much more annoying. I do understand. To find the inflection point is more annoying. But the key thing to keep in mind is when you find an inflection point, that's only your x value. You still got to plug it back into the original function to get the point. Anytime I want you to find a point, you have to plug into the original function. When you do a sign chart, it's always whatever derivative you're doing a sign chart for. But when we want a point, it's the original function. So another one of these. Find the points of inflection on f of x equals x of 5/3 in terms of the intervals where f of x is concave up and concave down. So same idea. So let's first take a derivative. A lot more annoying. Bring it down, subtract 1 off. So 5/3 x, common denominator, to the positive 2/3, sorry. Let me do it one more time. Bring that down, subtract 1 off to get the second derivative. Now remember, when you bring it down, you're going to get essentially 5/3 times 2/3 x, common denominator, -1/3. So I get 10/9 x and -1/3. Let's rewrite it for the sake of making it a little nicer. 10/9 times 1/x of 1/3. I brought it down. That's my second derivative. Now, to find critical points, a lot like find inflection points, a lot like find critical points. Right? It's where the derivative equals 0, second derivative equals 0, or undefined. Right? So this never equals 0, but it does get undefined. So undefined is the denominator equal to 0. And my denominator right there. So let's set that equal to 0. You can do the math, divide by 9, right? Cube both sides, x equals 0. So that's my possible inflection point. Remember, it's a possible inflection point, so I gotta see if there's a sign change there. So let's do a sign chart. Alright, I wouldn't be able to graph this one. I mean, it looks weird. So let's do a sign chart. My possible inflection point is at 0. I'm just gonna draw a line because I know it came from undefined. It's not a big deal though. This is the way I do it. So there's my possible inflection point. Let's hit the intervals that might be our answer. So negative infinity to 0 and 0 to infinity. Right, those are my two choices for concave up, concave down. Right after that, we pick our test points. So something to the left is 0, like -1. Something to the right is 0, like 1. Remember, this is our second derivative graph, right? It helps me remember where to plug my test points in. So I'm plugging into this guy. Now that is kind of funky. So let me rewrite it a little nicer. This is 10 over 9 to the cube root of x. Right, a little easier to plug it into, at least mentally. Just plug -1 in there. If you plug in -1, you get 10 over 9 to the cube root of -1, which is this 10 over 9 times -1, negative 10 over 9. So this is a negative. If you plug in 1, 10 over 9 cube root of 1, which is just 10 over 9. So positive. So there we go. This is concave down. This is concave up. So negative infinity to 0 is my concave down. My concave up is from 0 to infinity. And notice we go from negative to positive. There's a sign change. So there is an inflection point at 0. Now remember, you have to actually write the point. So it's 0. And then anytime you want to point, you plug into the original function, right? So if you want to point, go back to the original function. So you plug 0 into here. My mouse cooperates. You get 0 to the 5/3, which is 0. So that's my inflection point. Okay, next. Finding intervals of concavity and inflection points given a graph of f prime of x. For a lot of people, it's the hardest one. So I give you the graph of f prime of x. Let's do an easy one to get started. Since that effect, right? I want to do the graph of the second derivative. Remember how we figure out where the second derivative is? Because remember, concavity is where the second derivative is positive. Concave up is the second derivative positive. Concave down is when the second derivative is negative. So if I give you a graph of f prime, how do you figure out where the second derivative is positive or negative? Well, it comes from the slopes, right? If you're trying to take it, if you're looking at the derivative, anytime you look at a derivative, it's all about slope, right? So if this is my first derivative, and I'm trying to find the second derivative, first I find the zeros, right? The tangent points. There's my 0, where the slope is 0, and then over here, my slopes are negative, so I should be on the negative side. And over here, my slopes are positive, so it should be on the positive side. So does that let us know? That when our derivative has negative slopes, another name for that is decreasing, right? When the derivative is decreasing, that means when something's decreasing, that means its derivative is negative. So when the first derivative is decreasing, that means the second derivative is negative, which means it's concave down. When the first derivative is increasing, right? Increasing, decreasing just means basically what's the derivative doing. So when the first derivative is increasing, that means its derivative is positive. So that means the second derivative is positive, or concave up. Again, that's a tough concept for a lot of people, right? So if I give you the first derivative, you have to look at, okay, I'm trying to find its derivative. So how do you find derivative? You look at increasing and decreasing, right? Every time you don't have the function you want, you have the first derivative, I'm really need the second derivative, look at increasing and decreasing. Increasing means positive derivative, decreasing means negative derivative. That's all these words mean right there. Those means derivative. How about the inflection points? Remember, that's when the second derivative is equal to 0 undefined. So we look at a local extrema, right? We look at the min-max, like right here. Local min, it's a possible inflection point. You just gotta see the sign change, but that'll be easier with examples. So on this one, given the graph of f prime below, so these are both f prime of x. I want to find inflection points and concavity. So I want to find concave up, concave down, and an inflection point. Now in this case, we can only find the x values of the inflection point. We actually can't find the inflection point, which is something we can plug into, but we'll find the x values though. So again, we have the first derivative. So the way I do this is like, okay, we want to find inflection points of concavity. That's a second derivative stuff. I gotta think about the derivative of this guy. So I gotta think about increasing and decreasing. Right? And then if I want inflection points, I gotta look at the zeros. So let's look at the local extreme first for inflection points. Right? So those are the min and maxes. So I have a max right here at x equals -2. I have a min right here at x equals 0. Now, those are my possible inflection points. I have a possible inflection point at -2, I have a possible inflection point at 0. We'll talk about if there actually are. Before -2 though, what's going on? We are increasing. Right? And increasing means the derivative is positive. So that's concave up. And if you look at the middle part right here, we are decreasing. Because again, we're trying to find the derivative of this guy. So all you're looking for, anytime you want to find the derivative of a graph, increasing, decreasing. That's all we're ever looking for. Right, we're trying to go from here to here. So all you want to look at is for increasing and decreasing. That's it. So we're decreasing the middle here. So from -2 to 0. And then you look at the point right after that again. So from 0 on, we are increasing again. So that means our derivative is positive. So that's concave up, concave down, right? All about increase, decrease. So how about the inflection points? Well, does the sign change? I go from increasing here to decreasing. So yeah, it does change. That's an inflection point at x equals -2. And then it goes from decreasing here to increasing there. So x equals 0. If we want the point, the best we could do is this. -2 and f of -2. And then 0 and f of 0. It's the best we can do for a point because we don't actually have the y values. So that's the first example, right? A little tough, I know. A little tough. Let's do another one. Same concept. We want to find concave up, concave down, and then inflection points. Let's start with the inflection points, right? Because those are the easiest. It's the min and maxes are the possible ones. So we have one min right here at x equals 1. So that's my possible inflection point. Now let's talk about the graphs, right? Again, I have the derivative. I'm trying to look at the second derivative because I know increasing concavity is off the second derivative. So anytime you want to go from one derivative to another, you want to look at increasing and decreasing. Increasing means positive, decreasing means negative. Before 1, all this guy right here is decreasing. So that's concave down, -infinity to 1. After 1, all this guy is doing is increasing. So positive from 1 to infinity. And we did go from negative to positive, so there is an inflection point at x equals 1. Or 1 and f of 1 is our inflection point. I know, tough, I get it. It's the key thing here is know your definitions. If I have the derivative, and I'm trying to find the second derivative, the way you go from one function to its derivative is always increasing, decreasing. So anytime you want to go from a function to its derivative, always look at increasing, decreasing. I don't care if it's from f to f prime, from f first to f second, from the first derivative to the second derivative, if it's from velocity to acceleration. If you look at the graphs, look at the increasing, decreasing. Now we'll finish up with a fairly easy one. How to find numbers of concavity and inflection points given the graph with second derivative. So this is straight out definition, right? If I give you the second derivative, like am I hey, here's the second derivative. Where's the concave up and down, and where's the inflection point? Right? This is straight definition. So if you don't notice, I can't help you. Right? Concave up is where the second derivative is greater than 0. You have the graph of the second derivative. Where's it greater than 0 at? Right? From here and here. That's where it's above the x-axis. So these two values. So from -infinity to 1, 0, and then from 1 to infinity. Sorry about that. That's not much better. Concave down, right? Same idea. Look at the definition. Concave down is when the second derivative is less than 0. You have them in your definitions. So you have the second derivative. Where's the net less than 0? Right here. So from 1 to 2. Right? And then finally, inflection points. How do you find inflection points? It's when the second derivative is equal to 0 or undefined. And don't forget, you also need a sign change. So look at our graph right here. I know I've read it all up. Let me clear it off a little bit. Right, so here's where it equals 0. So that's where it equals 0. We got that. We don't have any undefined. Is there a sign change? Well, right here, I go from positive to negative. So yes, there's a sign change there. So at x equals 0. And there's a sign change here. We go from negative to positive. So both of those are inflection points. And that's the lesson.